In an attempt to discover geologic hydrogen reservoirs, this video establishes a connection between the presence of nano-magnetite and the presence of geologic hydrogen. Hot springs can be sources of magnetite and hydrogen. In certain geological settings, like hydrothermal vents, the interaction between hot water and iron-rich minerals, including magnetite, can lead to the generation of hydrogen gas. Up to now, magnetite was only considered as a catalyst for hydrogen generation. As it is one of the main, rock-forming minerals in iron-rich formations, in the vicinity of which hydrogen emissions have been detected, this work by Gaymond et al. Aimed to qualitatively assess the real potential of magnetite to source hydrogen during water-rock interactions. The work demonstrated that the generation of hydrogen from magnetite alteration was significant and exceeded generation from olivine-rich minerals. As for the future of native hydrogen exploration, these results demonstrate that magnetite-rich lithologies should be targeted while exploring natural hydrogen resources. Based on Gaymond's laboratory testing, magnetite is the primary source of hydrogen gas. According to an artificial intelligence overview, the presence of magnetite, in a hot spring, increases the probability of hydrogen occurring as a gas within that hot spring, especially if the spring's water is interacting with iron-rich minerals like olivine during serpentinization. This process can produce hydrogen gas as a byproduct. Serpentinization is a redox reaction between iron and water. Magnetite, a mineral composed of iron oxide, can be present during serpentinization. If magnetite is associated with a hot spring, it increases the likelihood of serpentinization, which on turn, increases the potential for hydrogen generation. Additional AI overview states that hot springs can be sources of both magnetite and hydrogen due to the interaction of hot groundwater with rocks and minerals, including iron-rich ones. These reactions can lead to the formation of magnetite and the production of hydrogen, sometimes associated with hydrothermal vents or altered rocks. All these AI overviews can be summarized into the statement that the presence of magnetite increases the probability of hydrogen occurrence simply because it is a hydrogen source. Based on the previous AI summary statements, consider the following hypothetical hydrogen exploration scenario. Well 1 is drilled into a carbonate reservoir rock. A very porous zone is logged, casing set and the zone swabbed to determine formation fluids. The swabbing produced only salt water with nano-magnetite dispersed in it. No gas shows were observed and the well was plugged as a dry hole. Additional geophysical data indicates well 1 was drilled in a down-dip location relative to the structural high in the reservoir rock. Knowing that hydrogen is 8 times lighter than methane and that magnetite is a source rock for hydrogen, the generated hydrogen should easily migrate up dip to the structural high. Consequently, well 2 was drilled into the magnetite-rich carbonate and a hydrogen reservoir was discovered. The presence of nano-magnetite in well 1 was like a smoking gun, telling the explorationist to drill up dip to find the hydrogen reservoir. The hypothetical hydrogen exploration scenario can be tested by drilling an existing hydrogen prospect called the Smoking Gun Hydrogen Prospect. In 2004, I participated in drilling a wildcat well into the Arbuckle Dolomite. After the well was drilled and casing set, a porous zone in the dolomite was perforated and swabbed to test for oil and/or gas. The zone tested black salt water that I initially thought was oil. The black material settled to the bottom of the drill pit and formed a black layer of magnetite. After additional geophysical and geochemical data was gathered, it was determined the well was down dip of the structural high and the magnetite that was in the formation brine was nano-sized as shown in the next slide. The nanomagnetite that was in the salty brine was analyzed using X-ray diffraction to determine its purity and scanning electron photograph to determine the size of the nanomagnetite crystals. The examination concluded the nanomagnetite was very pure and the crystals were indeed nano-sized, ranging in size from 20 to 60 nanometers. Normally, dolomites are considered a low porosity and low permeability lithology. When we swabbed the down-dip well, I was surprised to see the flow rate of black salt water being discharged into the drill pit. The swab zone flowed like a very porous and permeable zone, somewhat like a porous sandstone. The nano-magnetite crystals didn't impede the fluid flow. It flowed like flow through a high porosity, high permeability lithology with good, interconnected porosity. This response can be explained by a research paper entitled Hydrogen, Induced Transformation in Dolomite, Unlocking Natural Hydrogen Exploration and Subsurface Storage in Carbonates. The paper, published in the Energy and Fuels Journal, states, dolomite formations are abundant and well suited for hydrogen storage due to their favorable reservoir properties. Natural hydrogen has also been discovered within dolomite reservoirs globally. Results revealed significant dolomite dissolution alongside ankerite precipitation, with porosity and permeability increasing by up to 17 and 20%, respectively. Furthermore, the dolomite, ankerite transformation could be a key indicator for natural hydrogen exploration. A very significant conclusion coming from the laboratory work just presented from the Journal of Energy and Fuels is shown again at the top of this slide, namely the dolomite to ankerite transformation could be a key for natural hydrogen exploration. If so, the question arises, namely, does the Arbuckle dolomite that was drilled in the down-dip well contain both dolomite and ankerite and thus have the potential to be a favorable hydrogen reservoir? The answer, based on an AI overview, is yes. The Arbuckle dolomite can contain ankerite, particularly in the form of overgrowths or replacements within the dolomite matrix. The sequence of transformations that occurred during the generation of hydrogen are displayed in this slide. Beginning with the interaction of water with dolomite, iron-rich ankerite is formed as overgrowths in the dolomite porosity. Interaction of the water with ankerite produces nano-magnetite within the dolomite porosity as shown in the slide. The interaction of the formation water with the nano-magnetite results in the generation of hydrogen, which can migrate into a hydrogen trap. The Smoking Gun Hydrogen Prospect incorporates this sequence of transformations to form a structurally trapped hydrogen reservoir. This presentation establishes a geochemical connection between nanomagnetite and hydrogen in the Earth. This connection, combined with gravitational and geomechanical concepts, forms the basis for the Smoking Gun Prospect. A short video on YouTube describes additional geophysical and geologic evidence supporting the hydrogen prospect. It can be viewed by searching under the title Smoking Gun Hydrogen Prospect. I am looking for a company that I can consult with that is willing to drill a 6,000-foot test hole to prove that nano-magnetite is a smoking gun that can be used to locate shallow, white hydrogen in the Earth. I can be contacted at cancerout@ymail.com. Thank you.